Hello viewers, welcome to Coding Interviews channel. Hope you are doing great. If you haven't subscribed to the channel yet, please go ahead and subscribe. I have created bunch of playlists to cover various categories of problems such as BFS, DFS, dynamic programming, stacks, queues, linked lists, and so on. Please check them out. I have uploaded the code for this problem to the GitHub repository. You can get the link from description below this video. Let's jump into today's problem. All paths from source to target. Given a directed acyclic graph of n nodes, find all possible paths from node 0 to node n minus 1 and return them in any order. The graph is given as follows. The nodes are 0, 1 and so on till graph length minus 1. Graph I is the list of nodes j for which all edge ij exists, right? So basically we are given with a graph of n nodes. So the n nodes are labeled as 0 to n minus 1. So we are given with n nodes, right? N nodes. So nodes are labeled as 0 to n minus 1, right? So, and we have given with one more piece of information, directed. So the graph is a directed graph. That means if there is a edge from I to j, right, that means there is only a path from I to j. There is no reverse path, but that means j to I is not there as long as it is not mentioned. So that is what the directed means. So normally if in a regular graphs, right, we would think, okay, if there is a edge from node I to node j, you would think, okay, you could go from I to j as well as j to I, right? But in this directed graph, right, in this directed graph, if there is a node between I and j, you will be specified in what direction. That means will you be able to go from I to j or j to I, right? So that is what is directed. So in this particular case, our graph is a directed graph, right? So if we were mentioning, let's say there is a path from I to j, that means you can only go from I to j. The reverse is not true, right? That's the first understanding. And the second piece of information that we have is an acyclic graph, right? So acyclic means, so let's say if you start from a node, right, you will not be able to come back to that node. So but that means there are no cycles in that graph. That's what it is. So if you have bunch of nodes in the graph, right, as we are saying there are n nodes. So if you start from a node 1, you will not be able to come back to node 1 through some path, right? So that is what is acyclic, right? There are no cycles. Remember, these two are two good pieces of information that are essential in order to solve this problem. One is the directed and the other one is acyclic. So it doesn't have any cycles. So let's go ahead and look at the example given here, right? So this means there are like 4 things. So 4 adjacency lists, you can say. So that means this graph has 4 nodes, right? So as we said, nodes are named from 0 to n minus 1. When there are 4 nodes, the nodes are 0, 1, 2 and 3, right? So the graph is looking like this. There is a path from 0 to 1, just like what we said, right? So I to j, that means you can go from I to j only. Reverse is not true. So that's the thing you need to understand here. So there is a path from 0 to 1, that's it. There is no path from 1 to 0, that is a directed. And there is a path from 0 to 2, right? Again, here also the reverse is not true. 2 to 0 there is no path. 0 to 2 is the only path. And then 1 to 3 is the path and 2 to 3 is a path, right? So that likewise the directed edges are given to us, right? So that means there are some nodes, you start from 0 and end at possibly n minus 1. Some paths may not end at n minus 1, but in this example it so happened that all paths are ending at 3, right? But it may not be the case, right? So some paths may not end. So in that particular case, now our task is to find the paths not just one but all possible paths going from 0 to n minus 1. So the 0th node to the last node, right? So I have a like rough diagram here. So we have a 0 here and n minus 1 node. So you might have any like different paths in between those. You have to get all those different paths as an answer, right? So in the example on the left side, right? So from 0 to 1 there is a path, and 1 to 3 there is a path. So since we are tasked to get all the paths from 0 to n minus 1, so that means we are interested in the paths from 0 to 3 only, right? So 0 to 3, 0 to 1 and 1 to 3, that is one path. 0 to 2 and 2 to 3, that is another path. So that is what is given here, right? Output 0 to 1 and 1 to 3, 0 to 2, 2 to 3. So these are the two paths possible in this particular example, right? So likewise, we are asked to generate all the different paths starting from 0 to n minus 1. So the approach that we are going to use here will be a DFS based approach, that means a depth first search, right? So we will start from the node 0 obviously, because that is where we are looking to start the path from, right? So from then we do the DFS and explore one path. But while exploring, we have to collect the nodes that we are seeing in the path, because ultimately we have to return the path itself, right? We have to return the path itself. It's not just the number of paths, but we have to return the path itself. That means we have to keep accumulating the path, right? So, but what if a path is not leading to n minus 1, right? What if a path is not leading to the node that we are looking for, that n minus 1? In that particular case, when we go back, right, okay, we have to apply a backtracking mechanism, right? So we will remove that nodes from our path, right? So we went through one path, but we realized at the end, okay, that is not leading to the n minus 1 node. Then what we do? We backtrack, and we backtrack one node and see if we are able to proceed further. If not, we backtrack another node, we backtrack another node, like that. So this algorithm is going to be a combination of depth first search and backtracking, right? So we need to find all the paths. So at the end of the DFS, if we are able to get to the path or node that we are looking for, that is the node number is n minus 1, then we will add that path to our set of paths, okay? So that is the basic algorithm. So now let's go ahead and try to understand through the code, right? So we are given with the input as graph, right? So the graph is given as adjacency list, you could say, right? That means 0 is connected with 1 and 2. That means there is a path from 0 to 1 and 0 to 2. Again, since this is a directed graph, you have to only assume, okay, there is a path from 0 to 1 and 0 to 2. Reverse is not true as of now, because we have not gone through the node 1 yet. So node 1 is connected to only node 3. Node 2 is connected to node 3, and node 3 is not connected to anything. So from node 3 there is no outgoing path. So node 3 has only incoming paths, but there is no outgoing path, right? So that's what is our adjacency list is, right? So now what we are going to do is we will do the DFS. So that is a graph that we are given with, and we are declaring an answer. This is what is a list of all paths that we are going to return, and then there is a n, that is a variable, what is the count of number of nodes that are given in the graph, right? And then we are going to do the DFS. So we know the start node and we know the end node, right? The start node is 0, that's what we said. So end node is n minus 1, right? So we pass the start node, and in the path, since we are going to start the path at 0, we add 0 into the path to start with, and we pass the graph to the DFS. Now, so to see if the current node is n minus 1, if so, we just add the current path, whatever we came so far, to the answer and return from there. But otherwise, if the current index is not the last node, right? What if that is the case? Then we will be doing the DFS starting from whatever the paths or nodes that we can reach from the current node, right? So for each next node in the graph, we add the path that node to the graph and do a DFS again from there. So essentially what we are doing is we start at one node and we see if there are any paths possible from that node. So in this particular example on the left hand side, we start with 0. So from 0 we could go to 1 or we could go to 2. So that is what we are doing in this for each, right? So we first go with 1 and see if we go further. From 1, could we go any other place? Yes. From 1 we could go only to one more node, 3. So when we encounter 3, the current index is 3, right? N minus 1, then we add that particular path. So here I am doing the backtracking here. Basically, I am removing the node that we are adding into the current path, right? So that means, okay, I added the current node, I explored that node, but if it has reached the path or if it hasn't reached the path, I need to remove this current node so that it can go and process the next possible path, right? So that's what is the backtracking that we are doing here. So this is a version of DFS plus a backtracking, right? So let's look at the time and space complexity for this particular thing. So time and space. We already know there are n nodes, right? So, and how many paths are there in the n node, or how many paths are possible, right? So in this particular example, we are given with 1, 2, 3, 4 edges. That's it, right? But in reality, can there be more edges or less edges? If there are 4 nodes, are there only 4 edges? Since the number of nodes are n, it could be possible that there can be more number of edges possible. But in the case of 4 nodes, yes, it's only 4 paths are possible. But we could have a path from 0 to 3 as well directly, right? So if we keep on adding those paths, right, the number of paths you get is each node could be connected to n minus 1 other nodes, right, in the worst case, or in the best case, whatever the term that you put. So it could be a complete web of connected nodes, right? So in that particular case, there are n minus 1 outgoing paths from each node. That is possible at the worst case, right? So that means how many possibilities that we have at each node, right? So the number of possibilities will be 2 power n possibilities at each node, right? Since every node is connected to every other node, right? 2 power n minus 1 we could say, just for the brevity, right? Since every node is connected to n minus 1 node, so we could say 2 power n minus 1 edges are possible, right? So that many edges we might have to traverse potentially, right? But if we are saying every node is connected with 2 power n minus 1 ways, right? But we have n nodes, that means the total complexity would be n into 2 power n minus 1, right? So we said n into 2 power n minus 1, right? That will be the total time complexity. So this is actually 2 power, right, not n power. So we are saying there are n minus 1 nodes each node is connected to, right? And the number of possible paths will be 2 power n minus 1 for a single node. Since there are n such nodes, we will say n into 2 power n minus 1 is the time complexity. And space complexity. So how many paths are there? That is another question, right? And let's see if we are using any extra space here. So we are using a space for returning the answer. If you consider okay, only this space, right, that you are using. Apart from that answer, you are not using any other space, right? You could say order of 1, that is a constant time complexity. But since this DFS is going to be called recursively so many number of times, there is a stack space that will be used to maintain the recursive structure. So you need to account for that as well. So on the whole, the total number of space, so on the whole, when I am saying on the whole, right, it includes the answers also, whatever the space that we need to use in order to return the number of paths. As we said, there will be 2 power n minus 1 edges totally, right, and there are n paths, right? So in that particular case, how many paths are possible? Obviously there are n into 2 power n minus 1 paths possible, right, because there are n nodes and there are 2 power n minus 1 nodes connections, right, different ways of connections. In that particular case, we will say the time complexity and space complexity are same basically. So space complexity is also n into 2 power n minus 1. But of course, these are worst case time complexities, right? So if the example is very similar or simple that we are seeing from the left side, right, obviously it is much less than n into 2 power n minus 1, right? So but these are worst case. Since big O notation is always about the worst case time complexities, we will go with order of n into 2 power n minus 1 and same for space as well. If you have any further questions, please post them in the comment section below this video. I'll get back to you as soon as I can. You can find the code in GitHub repository and the link is in the description below this video. If you haven't subscribed to the channel, please go ahead and subscribe and share among your friends. Please click on the bell icon so that you will be notified about all my future videos. Thank you for watching. I will be back with another problem very soon. Till then, stay safe and goodbye.